to help understand where it's used and wasted and where savings are most likely to be made. So all fairly straightforward and sort of nothing new with all of this. So comparing with performance in previous years to monitor improvement, let's have a look at a more modern manifestation of that 1980s booklet. Well, we've got display energy certificates in use now. They use normalisation, degree days for heating fuel correction and occupancy hours. Interestingly, the DEC software only allows for an increased occupancy hours, not reduced. And in the current situation, reduced might be what you would need to do. It could be something ESOS-driven, where improvement objectives have been identified or opportunities have been identified, and you want to measure how effective that's been, or just any improvement projects from any driver. If you make a change like that, you really need to use normalisation to accurately assess success. If you're using ISO 50001, the energy management standard, that would require normalisation. It could be difficult to demonstrate continual improvement if you're not normalising. And in support of that, ISO 50006 explains normalisation. If you read all the blurb for this webinar, you'll know I'm involved in as a UK representative in the working group developing a new version of 50006. It's being updated to reflect the changes in the 2018 50001. So it's sort of produced with supporting 50001 in mind, but if you're doing any sort of energy management activity, it's quite a useful document to be aware of. You don't need to be using 50001 for 50006 to be useful. So just to use a bit of terminology from the standard, the old Offices Guide explained the use of EMPIs. Principles are unchanged, but the modern terminology talk about the energy performance indicator being a quantitative value that requires identification of a static factor. So in offices, I'll probably use offices as an example quite a lot because that's fairly widely applicable. We normally use floor area. It's something that impacts energy use. The bigger the building, the more energy, and it doesn't usually change. So that gives us kilowatt hours per metre squared as an energy performance indicator. So the 50001 standard says that you should establish an energy performance indicator and call it your baseline, energy baseline, using information from a suitable period of time, normally a year. And then if you have data indicating that relevant variables significantly affect energy performance, the organisation shall carry out normalisation of those performance indicator values. So that's a bit jargony. It's the wording from the standard. Relevant variables significantly affecting energy performance. Well, I've already mentioned degree days. It's fairly well established that there's likely to be a link between your heating fuel use and the outside temperature. So that makes it a relevant variable. But don't assume that it will be a relevant variable. It's likely to be, but it might not be. We'll come to that later. This is often done the other way around. The standard suggests the organisation should be monitoring data, looking for relevant variables and adjusting accordingly. What often happens in practice is that you're reviewing your energy performance, you've made some improvement projects, and yet your performance indicator isn't improving. That's probably a sign that there are some variables at play, some relevant variables, and you ought to be normalising for those. So you then work backwards and try and work out what they are. So you're a bit happy with your performance indicators. So this little text will pop up now and again just to reassure. depending on the nature of the activities, normalisation can be a simple adjustment. It doesn't have to be complicated, but it can be, depending on the scale of the energy use you're talking about and the number of relevant variables there are. So if you're monitoring your energy use over time, you should be looking for relevant variables. You need to identify them. Things that impact energy use but are not constant. They're changing over time. So as I've said, in offices, typically that would be weather, and then sometimes occupancy might need to be taken account of as well. And certainly with decks, both of those are built into the methodology. And back to a quick definition, normalisation, the process of modifying energy data in order to account for changes in relevant variable to compare energy performance under equivalent conditions. The reason I've put that in there is just to remind me to stress that when I'm talking to people about this, I do occasionally get involved in auditing companies operating 50,001 systems. And when I talk about normalisation and can they show me what normalisation they've done, I just get the sense that they're a bit nervous about it and they think I'm talking about something that in some way it just feels like cheating. You know, we've talked about calibrating meters and getting accurate data and recording it, verifying it, analysing it, and then I'm saying this 950,000 kilowatt hours, you should be knocking 10% off that before you compare it with your reference year. And I can understand them thinking, oh, hang on, that's not the real data anymore. You're doctoring it because it's there in the standard. This is what we need to do so that we're making an equivalent comparison. So as I said, typically correlation between degree day data and heating fuel use. I'll just try and illustrate this in practice. It's a bit difficult in the abstract, not a real case, but I'll have a go. Put simply, the bigger the degree day number, the colder it has been. And in a short webinar today, I'm not going to attempt to explain how this is calculated. Broadly, it's an average temperature for the day, but it's slightly more complicated than that. But if we settle for the average temperature, we'll go for that. So the colder it is, the lower the average temperature is, the bigger the difference between the average temperature and the temperature the heating's going to come on. So you get a bigger number, and you add them up over time. Bigger the number, the colder it's been. But we've talked about monitoring your energy use. So we've got a quick illustration here, an example of something from the standard that shows that in the winter, your heating fuel goes up and your cooling energy consumption goes down. Just in case any of you are looking at that and the first impression you're thinking there's a mistake there, they've got winter in month 7. July's not winter. I'll preempt that question and just remind you this is from an international standard. We might be used to July being summer-ish. But if we were in New Zealand at the moment, we'd be in midwinter. So stuff in the standards tends to get presented generically, not UK specific. It's a bit of a luxury that the normal language is English, although it tends to be American English. I have attempted to make all the Z's, S's in my slides. Apologies if I missed any. So that's the idea. If you see something like that, you're seeing something that is a relevant variable. It's not a flat line. So something is happening and it's something you might want to correct for. So how does that work in practice? We'll talk about a hypothetical reference year where your degree day number was 2,500, but the year you're currently looking at was milder, so a smaller number, say 2,000. You need to normalise your performance indicator by that ratio. So 250 kilowatt hours, if that's what your actual consumption had been, becomes 312. you're in a colder year. So what you've done is you've artificially increased your figure. Sorry, you're in a milder year, so you've artificially increased your figure. I said this would be difficult in the abstract. So you're making a fair comparison. So this is what you would have used with similar weather to the reference year. You only used 250 because it was a mild year. But if it had been an identical year weather-wise, you'd have used 312. So if your reference year was 320, you can see that you've demonstrated a modest improvement. If you simply use the 250, well, actually, is that a bad thing? You'd look good, wouldn't you? Our consumption's gone down from 320 to 250. Haven't we done well? The trouble with that is if you're still monitoring next year, and next year's a cold year, you're going to look very bad. So it's worth getting it right year by year. You might get some short-term benefit, but you'll look bad in the long term. Because this is what happens when you get a colder year, say 3,000 degree days. So your 250 would then be adjusted the other way. The ratio is inverted, so you end up with a figure of 208. So that's what you would have used in the reference year. You've used 250 in the cold year, but you'd have used 208 in your reference year. So if your reference year figure was 200, you've had a slight drop in performance rather than a major drop. So it's a more accurate reflection on what's actually happened. And you need to do this for a number of reasons, really. But just to be clear, all the way through those examples, your actual consumption was 250. You know, that is what's being paid for. That's what's being reported to the board and so on. But when you're doing your energy performance indicator checks, you need to make these corrections, call them adjustments. They're corrections to normalize the situation, so you're making a fair comparison. In the example I've used, I swung 20% high and 20% low. That is at the extreme end of the range, but you do get that change from year to year. Not every year. Sometimes there's not much change from year to year. It doesn't make a lot of difference to the results. Sometimes it's 5%, sometimes it's 10%, but it can be as much as 20%. So that's why I use those figures in the illustration, just to make the point that it can be a significant difference. If you're using this technique across a number of buildings, if you own buildings across the UK, it's also worth being aware that there is a difference north to south across the UK. And there's a 20% variation north to south. So if you're running identical buildings in the northeast of Scotland and the southwest of England, you could be spending 20% more on your heating fuel in the northeast of Scotland. That would be normal. So I've spoken a bit about offices, but of course energy is used in lots of other ways. Floor area will not always be an appropriate static factor. So other examples, and there's lots of examples in the 50006 standard that I've mentioned. It could be the number of occupants or users, it could be the number of products manufactured or volume of product or volume of raw material. I've visited companies using volume of raw material in food production, volume of manufactured product in other areas. Could even be miles per gallon for transport. We're all familiar with that sort of non-metric terminology. So if you're looking at normalisation for manufacturing energy use, industrial energy use, transport, it is a bit more of a challenge than buildings, because things like degree day data is available from third parties if you're dealing with an office building. But if you are looking at a manufacturing situation, you're sort of starting with a blank sheet of paper and you need to compile your own data to apply normalisation as appropriate. So I've said degree days are easy. What about the rest? I've also mentioned 50,006, so let's just have a quick look there. There's a number of appendices with lots of good practical examples. Appendix D deals with normalisation. Just to recap, the process of modelling energy consumption with respect to relevant variables in order to compare under equivalent conditions. It says typically statistical methods such as linear regression are used to normalise or model energy consumption with respect to relevant variables. So that sounds a bit heavy going. Modelling energy consumption just means identifying a relationship, as in a mathematical relationship. So you're looking for a mathematical model, energy use changes by 10% relative to whatever the variable is. So, y equals 0.2x or something like that is what we're talking about there at the simple end of the range. Of course, it could be a lot more complicated, as I said earlier, with multiple variables, but don't be put off by that slide. It might require statistical methods, or it could be a bit more straightforward than that. Things like linear regression can be done in Excel, so it's not suggesting you need specialist software either. If statistics is something you thought you'd left at the gate when you last left college, the bad news is actually we do need to use it sometimes. But if it is a bit like a foreign language, it's probably best to talk to someone who's using statistical methods all the time and get a bit of help. This is also from the standard and is drifting into the sort of explanation of where you might be using statistical methods. Just put it in there to show you what's in the standard, really. And again, we don't have time to start going into details of how we would do this, but there's an example of the model. E is energy is a function of the relevant variable, and we've got a plot here with production and energy consumption. If production is up and down, so that is a little bit a wavy line, and your energy line was flat, then the variation in production is not a relevant variable. It's not affecting energy use. If the energy line is waving around a bit as well, and it's dipping in the same sort of places, I'm oversimplifying a bit here, but time being the imperative, if it appears to be following dips in production, then it's probably a relevant variable, and you need to quantify it with that model. Energy equals a function of the relevant variable in order to make the correction. So I said this would appear now and again, and I thought following that slide, it's probably worth repeating. Depending on the nature of the activities, normalisation can be a simple adjustment or a more complex procedure. The standard there was talking you through the more complex procedure, but it can be simplified. So I always like to try and keep things in perspective. What happens if you don't normalise? I was kind of hinting at that with the illustration with the degree days. If you don't normalise, you don't know the true situation. You may be overestimating or you may be underestimating. So if we're talking about a particular project, you've got the risk there of thinking the project was a great success, or you might be thinking it was an unmitigated disaster without that normalisation. And if it's the wrong decision, you'll make the wrong decision about repeating the project elsewhere. If you thought it was a fantastic success and it wasn't really, you'll go repeating it when you shouldn't be. If you think it was an unmitigated disaster, but actually corrected, it turned out to be not so bad, probably worth repeating, but without that correction, you'll think, better not repeat that. So that's what happens if you don't normalise. You'll make wrong decisions. And in terms of ongoing monitoring of performance, you might miss a problem developing. You might not see performance dropping off because the variable is counteracting the drop-off in performance. And of course, if you are operating a 50,001 system, and anyone using a significant amount of energy really should be, you'll find it difficult to keep demonstrating continual improvement. So if the numbers are in your favour in 1 year, it'll help you show continual improvement, but the likelihood is they'll be in the opposite direction the next time you look at it, and it'll make it difficult going forward. The whole point of 50,001 is you don't take your eye off the ball, you continually monitor performance. So keeping it in proportion, as I've said, full statistical analysis may not be appropriate for a small project. However, you do need to do something. You will make incorrect decisions somewhere along the line if you ignore this. You will need some sort of model, some sort of mathematical relationship from analysing the data. You can't rely on a hunch, although you may well start with a hunch to decide where to start looking at the data. You can get it wrong relying on hunches as well. So have a good look at Appendix D of ISO 50006. I've referred to that quite a bit today. But also have a look at the CIBSE energy benchmarking site. That's an interesting site. You might like to take part in that. It's a live data analysis experiment. You may already be participating. I'm referring it to you particularly for the references at the bottom of the page, the sort of thinking behind the project. There's some good reads in the references at the bottom of the page, which you will find there. You don't need to worry about that. You'll get these slides and the link. That's well worth a look as well if you're working in this area. So I said don't rely on hunches. It's not always appropriate that the obvious things need correction. You know, I've said the weather affects heating fuel. My slide did say typically. It's not guaranteed to do that. In some buildings, many modern buildings, very well insulated, heating energy is less than 5% of the total energy use of the building. So even in an extreme year where there's been a big change in the weather conditions, it could be that 20% extreme, but only of 5% of your energy use. So a 1% variation overall. It's starting to be not so significant and not influencing your decision making too much, and you may not want to worry about it. Say if it was a 10% swing year, that would be 0.5%, 5% swing year, even less. In some manufacturing installations, there's a lot of heat that is unavoidably lost from the manufacturing process, which is heating the manufacturing facility, and very rarely is the heating needed to top up on that. So again, the effect of the outside weather doesn't really have much effect on the heating energy because there isn't very much in that sort of building. So a lot of the time it is, but don't assume. Have a look at the data. And if your heating consumption isn't changing between March to June to October to December, then it's not a relevant variable. The other one that's used in decks, extended occupancy hours. At first inspection, that might seem a bit of a no-brainer. If you start out with a building being used 8 hours a day, and that's your reference year, and then later on you start using it in the evenings, so it goes to 10 or 12 hours a day, you'd expect the energy use to go up because you're using it for more hours. But what about if there's no zone controls? What about if the building was being used a bit, but not enough to really trigger thinking about normalising for extended use? I mentioned this is in the deck methodology. The guidance there is you only justify normalising if more than 25% of the area is being used for those extended hours. So let's just think about a school where a very conscientious headmaster is staying behind every day and working into the evening, and he doesn't like getting cold, so he's got the heating set up to stay on. He can't control it just for his office because they haven't got zone control, so the whole school is being heated. So officially it's got the shorter hours, but actually it's being run for the longer hours. They then start hiring out rooms in the evening and say, oh, we're officially open for longer hours now. We'll correct for those longer hours. Well, if you look at the data, you'll probably find the energy consumption hasn't changed because it was on all the time before anyway. A bit of a dig at the DEC methodology there, because DEC methodology doesn't ask you to think about it that closely. It just says if you're using more than 25% of the area, normalise. And I say you might well have been using your full heating capacity all the time already, and you'll be, in that case, you would be falsely correcting the data. So on to the DEC community to think about. So we are in a new normal. That was my idea at the start of the presentation. How have businesses changed, and how does that impact energy use? The energy use, as I said, it will be what it is, but we do need to evaluate performance for all the reasons already stated, so we do need to make corrections. Where can we look at for guidance on where we might go with this? Well, let's look at SIBSE's post-COVID advice for mechanically ventilated buildings. The suggestion here is that we increase air change rates and keep it running all the time. That suggests increased energy use. Can that be modelled? Can we start recording that in detail and see the effect of that? Or if not, can we calculate it? If we're not metered in the way that we can separate that out, can we calculate it and model it that way? That might be worth looking at. How's industrial energy use been impacted? Well, I've spoken to a few people who've modified their working patterns. They previously had 24-hour production with 8-hour shifts, with crossover between the shifts. To keep production going, they've changed that so that one shift disappears and then another shift starts, so that people will never meet. It means that the production line is running without actually producing any goods. So if your performance indicator is kilowatt hours per kilogram of raw material, I've seen that being used in a pizza production facility. There would have been downtime previously just while they changed product range, different mix of material and so on, but they wouldn't have had it shut down for an hour. We're talking thermal stress being the problem here. You can't just turn all your ovens off for 10 minutes and turn it back on again. Even for an hour, your cool down period and warm up periods are too long. So they're going to keep running, but they're going to have 3 hours out of 24 where there's no product output. So that is bound to affect the kilowatt hours per kilogram of raw material, because for 3 hours they won't be converting raw material. But as I said before, we can't assume it's a straightforward linear relationship. You need to look at the data. They've probably got data for periods when they do shut down for shorter periods, and they can probably work from that and normalise accordingly. So yeah, there is normally a way. It's not always straightforward, but you should be able to do something. A normalisation factor can be developed, maybe going back to that sort of process. I won't dwell on that. So what happens if you decide that despite your best efforts, you just can't normalise, you can't get the data, you can't work out what the correction factor should be? Well, we've got to accept that reality occasionally. So for one-off projects, be aware of the limitations, try and estimate it up or down, and explain. Include an estimate of confidence. You know, don't ignore it. Explain the limitations of what you've done. So if you're dealing with 50,001, it would be the same. At least try and explain what you've done. If it's a bit more pronounced than that, if it's not a one-off thing, if it's a more permanent change, and I guess we don't know at the moment with the lockdown situation. We've probably had the situation in March and April and May, and then it might have changed a bit in June, July and August. It might change a bit more later in the year. We may go back to normal in 2021. We may not. We may be talking about a more permanent change. Well, as you'd expect from a good standard, all eventualities are covered. So the standard does talk about using energy performance indicators and comparing with a reference year, but they do also say, if the performance indicators no longer reflect your energy performance, or if there have been major changes, start again. You don't have to keep referring back to the same reference year over a long period of time, and the standard does talk about that, so that might be worth having a look at that. If today's webinar has created an interest in 50006, you might be interested in the webinar that we ran in 2017. Details are still on our website as per that link, so you can have a look at that. I think we probably need to wrap up here and allow a bit of time for questions. So just in conclusion, if the post-COVID-19 changes are temporary, you need to establish a normalisation protocol, simple or sophisticated as appropriate, and just carry on as normal, having normalised for this year. If it turns out the changes are permanent, the new normal, it might be more realistic and permissible in 50,001 terms to start again. We'll draw a line under where we are and sort of set the data collecting again and start with a new reference year going forward. So that's going to make 2020 an important baseline year for energy management practitioners. Although actually more likely, as I was just rehearsing, we've had different periods already during 2020, and 2020 is probably not going to make a good reference year. So we might have to just try and normalise for this year, and then if things are a bit more stable next year, set the reference year again for 2021. Okay, so that's my concluding slide. I hope I've given you some food for thought there and some pointers to ask the right questions, and hopefully we can bounce through this year and normalise appropriately and not interrupt the good energy management work that's been going on for some time. I'll now have a look at what questions we've had.